so for some reason in the schedule for exam session, exam is scheduled for 18th. I don't know if you looked at it, but I think I will talk to the office and try to make it on 25th. So the plan is something is better. I don't know.
Yeah, I suppose like translation is started, but it's just black screen. Can you turn it on or something like that? Video тоже?
Yeah, thank you very much. Yes, so the plan for exam is as before. Okay, on 25th, I think we'll not have anything else then. And I just cannot like feel in myself like an exam, and lecture, and seminar.
So like if I don't attend an exam,
yeah, just skip. Yes, another question is how to grade seminars. So when I come up with this scheme, I didn't know that there will be two types of students. So I think for those who will need their grade on May, so for seminars, maximum points will be 2 times the number of seminars before exam on May. Yeah, so today is 13th. Yeah, 14th, yes. And for others, I don't want this extension of the number of seminars to be like to play against them, but rather for them. So we kind of, you can choose between 2 grades for seminars, either one that is like at May, or you can continue, right, and improve that.
Sorry
yeah.
for graduated students. When is deadline for us? No, for?
When is the deadline for what?
No.
So exam will be on 25th. I know that I have to give you the grades on 27th. 27th or before, so something like this. Yeah, last seminars for those who, like official last seminar, so you still can attend, and according to the poll in Telegram, people still will be attending. So yeah, so last seminar, like graded seminar for those who will take exam in May is next one. But what other space courses do with this usually?
Usually they just finish.
They just finish. Okay, maybe I
And maybe
should
there
have
are some
done this.
lectures after that.
Okay, we'll see. All right. So okay, have some people who. Okay, so Alex, maybe you can do number 1 then.
So we have
If you can use the microphone.
Hello.
Oh, you can. So maybe it's the way. Usually we
So we have a module M over a commutative Lie algebra H, and M splits into a direct sum of weights decomposition, so M of some weights, but M might be infinite dimensional, and we have a submodule M prime, and we want to show that M also splits into a weight decomposition, and it's just the restriction. So what we want to show is that if we have some vector, and we can write it as it will be a finite sum, so it will be something like lambda 1 times v1 plus lambda 2 times v2 plus lambda n times v no, not lambda, something like v1 plus v2 plus vn, where vi lies inside a m prime of lambda I, and it will be a finite sum. So we want to show that v, say just v1, also lies inside this submodule.
M prime is some module,
Yeah.
but maybe the I lies in M of lambda I.
Yeah. So
Not M prime of lambda I.
yeah. So this is what we need to show,
Ah, yes, okay.
and if we show this, we're done. And the strategy is to find some h here. We can find some h here, so that lambda 1 of h. So we can look at it in terms of vector spaces, universal enveloping algebra. It's sort of the same, because the universal enveloping algebra is just the symmetric algebra. So it's, but in terms of vector spaces, we want to find such a h here, so that h1 is different from hi of lambda I of h for all I greater than 1. And we can find this h in here by induction.
Why we need to find such lambda h?
Just because then we can take the powers of it, and it will generate some, then we'll be done. So first we need to find this h. We can find it by induction. We find the h so that lambda 1 and lambda 2 are different. Then we find the h so that lambda 1 and lambda 3 are different, and we can take a linear combination of them so that their sum is different, and we keep doing this so that we can find the h so that they are all different from the first one. Then we look at h of. Yeah, why we can find such a h. So first we find a h so that h of lambda 1 of h and lambda 2 of h are different. So it's some vector, I don't know, a1, a2, but then the next one could be the same. So just take the first one where we get a1 again.
So what are
It's h1 is, no, it's lambda 1 of h, so hi is lambda I of h. So we just pick a h so that we have a1 and a2 is not a1, and then we have a3, and if ai is equal to a1, so we have a1 here. Then we pick another h so that these two, another vector so that these two are different. No, not if we take if we take b1 times this one and b2 times this one. And this is, I don't know, a1, a3. This can be anything, but if we just take a very large linear like if we just take b1 to b1 and b2 to be very large, then these two and these two are going to be different. And we keep doing this. Should I write it more carefully? Okay.
Yeah, we have a lot of choices.
Yeah, we can. we just make B2 super large, but the- I can, yeah. Yeah. Yeah, yeah, yeah. Yeah, yeah, yeah. And then we take linear combination of all of them. Yeah.
The set where set of h, where lambda I of h and lambda j of h they coincide for some ng is a union of hyperplanes. So it cannot be from space.
Yeah.
Affine hyperplane.
Yeah, yeah, yeah.
Or not affine.
Fine, yeah. So we have this h, and then we look at we look at v, and we look at h of v, and we look at h squared of v, and we can see this is just the Van der Monde matrix. H cubed of v. So we get some Van der Monde matrix when we write v as linear combination here, right? So let's again say that just use this notation. Then v1 is with coefficients 1 all the way. This one is a1, a2, n. Yeah, yeah. And so on. Or we can just look at it as vectors. It's the same strategy. And by non-degeneracy of Van der Monde matrix, some of these AIs greater than 1 might be the same, but that's not a problem for us. So we can choose a linear combination so that we get 1 here and 0 here. So we have some element, something that looks like b plus b0 plus b1 of h plus b2 of h squared in the universal enveloping algebra. Van der Monde matrix. For just these numbers. Yeah. Plus b n h n. And we apply it to v, and we get v1.
I'm sorry, I kind of lost.
So this is h of v, the coefficients of vi's in v. This is coefficients of I in h of v. This is coefficients of vi in squared of v. And by the non-degeneracy of Van der Monde matrix, we can choose some linear combination so that we get yeah. And we get some element of universal enveloping algebra, and we apply it to v, and we get v1. And that's yeah.
Okay. I want to start with choosing a good basis for G. So the basis will be the following. We take H1, H2, etc. HR in H, such that this is an orthonormal basis of H.
Yeah, it's orthonormal to bilinear form, yeah.
Yes, yes. And then we choose EIs in G alpha I and Fi in G minus alpha I. And we assume that alpha i's are positive roots for some polarization. And then I claim that the Casimir element is the following. It is the sum from 1 to R of H I squared. This is because it is an orthonormal basis of H. Plus the following sum. Alpha I, EI Fi, plus Fi EI. This is because
So you have particular scale product.
yes, I use just the standard notation when the scalar product of EI Fi is 2 over alpha I.
Yeah, and this sum is not to the R, it's just by all
To
positive
N.
positive.
Overall positive roots. It is not I, it is
It's
some N. Yes. Then I'm going to compute how C acts on the highest weight vector. I claim that C of V lambda is the following. It is the sum of lambda of H1 squared plus the sum for I from 1 to N alpha I divided by 2 lambda of H alpha I. I'm going to write what this is applied to V lambda, where H alpha I is the commutator of EI and Fi. I didn't use the notation HI because I already used it. So I denoted it by H alpha I. Well, the first part of the sum must be clear because HI acts on V lambda by the scalar lambda of HI. And as for the second part, we know that EI applied to V lambda is 0. So Fi EI applied to V lambda is also 0. And for EI Fi, we write the following. EI Fi is applied to V lambda is Fi EI applied to V lambda plus the commutator of EI and Fi. Applied to V lambda. And this thing is 0, and this is exactly what is written here. And also we have this coefficient. And we now know that C is in the center of is in the center. So if it acts by if acts by the scalar on V lambda, then it acts by the same scalar on the whole representation, since the representation is reducible.
So it is what is in the right in the second sum. So EI commutator is H alpha I,
Yes.
right, times something.
Yes. Yes.
It's exactly H alpha I. Yeah, because
It-
of this.
Yes. Well, we know that since our representation is reducible, then C acts by the same scalar on the whole representation, and we just it remains to show that this scalar is exactly the scalar product of lambda and lambda plus 2 rho. So I need to check it. First, I claim that the scalar product of lambda lambda is this thing. And we can show it explicitly if we write something like this. We can write lambda as the sum of AI HI star, where HI star is the dual basis of HI. Then lambda lambda is the sum of AI squared. And also, at the same time, lambda applied to HI is also AI, because HI star acts on HI by 1 and on other HJs by 0. So from here it follows that this equality follows. So it's quite clear. And the second claim, which finishes the proof, is that the second sum is the scalar product of lambda and 2 rho. And we can show this like this. First, we know that lambda applied to H alpha I is the same as lambda applied to H big alpha I divided by alpha I. It is the definition of H small alpha I. Then we can rewrite it like this. And now we need to recall that H big alpha I is the element which is identified with alpha I when we identified H and H star. So this is exactly 2 divided by alpha I, the scalar product of lambda and alpha I. And now, if we rewrite the sum, alpha I over 2, lambda of H alpha I, we must write this as follows. These terms cancel, and we have the scalar product of lambda and the sum of alpha i's, and this is exactly 2 rho. So we are done.
Well, it is obvious that one root of maximum height exists because we have a finite set of roots. So
yes.
yeah, so we need to check that there can be more than one. Okay, assume. So I want so we know that if we add some simple root, we will get 0. Or we will get a root that is not in our. It's not a root. And same with beta. So I want to take vectors from these spaces, and they are singular.
So you like using the surf figure again. Well, this problem was only in like some reduced
Yeah.
root system. You use.
Yeah. We can use it here. Okay. Okay, so now let's take spaces this. And there will be representation of maximum height. So if they coincide, then alpha is equal to beta. Okay, because we have only one vector of axial height in these representations, and if they are not coincide, then they do not intersect. And then the system is reducible. Because we can apply n plus and have a beta and alpha. Or we have this vector and this vector by we can apply n plus to L beta and get and get a vector v from L alpha. So then they are equal. Like if they have a common path, then they are equal at all.
What's the problem if they have common path?
Then they are equal at all, like, because we can apply n plus to them and to get all vector, and we get both v and double v.
But sorry, why v to apply n plus?
Well, assume that they have an intersection that is not 0. Then we can apply this and we'll get and v and double v. It's not.
Why v is contained in plus and
Well,
Because we assume that this intersection is not 0. So the intersection is
well, like from any vector. That's not true. Not from any vector in L alpha we can. But by n plus we can go to v. Like there's could be other singular vectors apart from v and v in L alpha.
or we can obtain 0.
What do you mean?
How do we obtain 0?
Yeah, so
We apply something, right?
Yeah, we apply
Yeah.
n plus. So we.
Yes, but we can at some point obtain just 0.
Yeah, that's what I'm talking about. Yeah. It could be singular vector.
So then there is also one singular vector.
What?
Okay, so have more than one singular vector in.
Yeah, that's well in model in Verma model we always have
Yeah, yeah.
usually.
Here they are. It's my sigma. Yeah, but I don't think you actually need all this, right? Yeah, yeah. I mean, something was said and yeah. You don't need to consider intersection, do you? So you take L alpha and L beta. These are two highest weight modules of G, right?
Yeah.
And they are inside G, they are inside of adjoint representation. There are some modules of adjoint.
Yeah.
And root system is irreducible.
Okay, yeah.
So therefore, adjoint representation is irreducible.
Yeah, so they need to be to
So
coincide.
therefore they
Yeah.
should coincide.
Yeah.
So you don't
You don't.
If you have a reducible root system, then adjoint representation is reducible.
yes, it corresponds to simple.
Yeah,
You don't need to prove this.
simple. Irreducible. Yeah, okay, understand.
We kind of discussed it. I don't know to which detail we actually proved that.
Yeah, I suppose what is said about
Yes.
this should be simple.
Yeah.
Okay, thank you. Okay.
Well, we have two modules in adjoint representation, so they coincide because it's an irreducible representation. There are submodules of adjoint representation.
Then they are this representation. Right?
Yeah. So they coincide.
They both.
They both this representation.
In any which representation?
Finite dimension.
No. Well, you can take direct sum if it's irreducible, then yeah, sure.
Irreducible.
In irreducible, yes, it's only one.
I think I'll prove.
Yes. Very well. Okay. People didn't like number 4. What was that? Supposed to be some pictures, but okay, Всеволод, may I ask you to show that? So this is just some illustration. So we kind of did it for for those who were in spring semester with me. We kind of did it for SL3. So the idea was to look at this picture for B2.
It's a problem that was stated that we can take any root. Yes, we don't need for both fundamental weights. We could take any. Okay, I did only for one.
Actually, one is easier than the other. I can you can take the general statement. Now we would like to see an example. Yes.
So it's
So find point row, find point shifted action. Yes. So this one is
this are roots of reducible representation for this weight. The weights of probably on another.
what's the second picture for?
It's for the.
I think you can.
We need to find also to picture shifted action weights.
Only have for non-trivial weighted subspaces, yeah.
Yes. For other one, you have also something in the middle, kind of overruled test. The other one is this one, right? And you have another. Okay, so we are doing. We are trying to find the well orbit of the shifted action velvet, right? But for that you need rho, right?
We need to compute dimensions of the RAM model is weight and for this model that is isomorphic to the sum of
I'm sorry, did you already draw S1 and S2 for the one?
yes.
Can you
This one is shifted by 2 alpha 1s here, and this one is
but how do you get?
you could just compute explicitly the shifted action.
But shifted action is what? You take W1 plus rho, right? Then reflect, then subtract rho.
We reflect with respect to alpha 1 and then also subtract 1.
Subtract alpha 1.
Yes. On the, I think we did similar computation on the, in the last problem on the previous or on the previous. Yes, previous seminar. Yes, so weights so for this one it's obvious that it will be, for the views of weight it's obvious that it will be equal to 1 since these singular vectors have height less than v1. And so you get dimension 1 for this space.
In L lambda dimension is 1, yes.
And we want to compute dimensions of M lambda and dimension of this relationship.
Yeah, we at least would like to check that all these points are there.
All these points in
In L lambda, yes. In M lambda quotient by yes.
Yes, also. I just wrote the answer.
Okay, so what we are
Computing dimensions for this one, and it is was said on the previous seminar that dimensions of these weights of spaces are number of ways to so nu is equal to alpha minus sum of some positive roots, and it is and the dimensions of weight spaces are equal to the number of ways to decompose this into the simple roots. So this one is 1. For this is only no for this root it's alpha 3. So on it's only 1, 2 because we just subtract alpha 1 for this should okay, this one alpha 3, this one is alpha 2, alpha for this root we subtract alpha 3, which is equal also to alpha 2 plus alpha 1, so there are two ways, dimensions 2, and for the fourth root we subtract this alpha 4, which is alpha 2 plus 2 alpha 1, also equal alpha 3 plus alpha 1. So there are 3 ways.
So it's called Fermat model, yeah? Dimension of
Yes, for this, for Fermat model with
in this way.
weight v1 for the sum. Yes, 8 for that for mu1 is equal to 0 since it has height less than v1 for the both of them are 0. For mu2 one of them equal to 1 and the other is equal to 0 because mu2 we can get from the s2 times v1 by subtracting alpha 1, and from this one we can't get to this weight by adding positive roots, so it's 0. And the dimension of the factor is equal to 1. So next root is for the next weight is also so like this, and
so we have 3 Fermat models actually. So one from this goes like that, and shifted action of S1 and S2 are this, and we quotient by this. Okay, so we would like to. So of course these 2 points are here with dimension 1, so nothing here to check. So what about these 2 points?
You only need to check in the that's
For M3, for M3 there should be 0 and 0.
for M3
For
mu free. No, we can get from no, okay, yes, of course.
But everything is right. There should be 1 minus 0, yeah. Yeah, makes sense.
Yes. And for the next, for the last one, we also need to check that this sum is direct. But it's obvious since
Oh, this sum is with if you write mu, yes, is
for the mu4.
For some particular
Uh,
in general.
one. One get by 2 here. Yes. So it's equal to 0 because we can interchange E and F because indices are different. So it will be equal to 0. It can be equal to the 1 V2.
What is last about? What is it? V1 up to V1?
We need to check that if that vector for this space and for this space are not linearly dependent. We check that we can't get from this vector back to the yes, in U4.
Okay, I understand this better in pictures. So again, so this all this PGG resolution that we'll discuss today as well. So it's a part of it, right? So you actually quotient this Fermat model by this, and you get only these 4 points. So this is how you get irreducible finite dimensional out of Fermat. So this is how picture looks for V2. Right. So of course in this Fermat, these 2 weights have dimension 1. When I quotient by this, they are still dimension 1. So these are easy points. What about this 2? In this Fermat, it has dimension 1, but in white Fermat, it is of dimension 2. So it has only 2 paths going through it.
So like
Yes.
PBV. That's what how we can go. What's like in
No,
A2?
actually PGG resolution is much deeper result, which calls like what's the intersection, how they intersect further. So now we kind of deal in the like first couple errors of this resolution. Yes, which is like to 0 and then quotient.
So yeah, I want to ask what our PBV basis?
PBW basis. Yes. Yes. So we need to choose, right? That. So we go by. So this is alpha 2, right? So I go, I guess, by negative alpha 2 first. Then, so how much Yeah. So let me try to do this. So first, I guess I go by right. So I need to numerate. So this is 2, 1, 3, and this is 4.
So you want like something 2, 1, 3, 4 from right to left.
I would like to have sorry. 4, 3, 1, I guess, or something like this. So first I go like yes.
With 4.
Yes, first I go with 4. Then I go with like this. Then I go right by negative half of 1.
Half 2.
Oh, I guess. But anyway, so I will go first like that. I don't go down. So this has multiplicity 3, and I kill it by something from this. No, from this. Good. We need to check that they are actually different vectors.
Yeah.
And that's what actually feels. I just wanted to look at this picture. Like that's how it works. Like in this.
Can we understand everything from picture?
For very simple representations, we can. I actually, if you are persistent enough, I think you can see, I guess, that it is finite dimension. But I started doing this, but kind of didn't like that.
We should consider only kind of adjacent.
Yes,
vertices,
yes.
right?
So you just check all these points around and see that they are cubed. But it's already kind of, for SL5, it's not pleasant.
They will intersect on this.
Yeah, you need to check all that they do not intersect. Well, for this point already, you need to check something when you compute these dimensions. What about this point here, for example? There already might be some intersection in this Verma modulus.
Yes.
Or you need to use like Harishchandra, which we covered only for SLM last semester, to actually see where they can intersect. So the answer is not, you cannot, I guess, see everything from the picture, you can just see something.
But are there theorems from which we can see everything? I mean, well, how for all weights, how Verma modules, which are submodules of initial Verma modules, will intersect and.
Yeah, I think you can. I think you can build, like you can see on the picture, at least that intersections should happen on a shifted or on a shifted orbit, on the orbit of shifted action. This you can do.
Yeah.
So if you see, for example, that if you assume that they do not intersect there, then you have multiplicity too much, like in an original Verma model.
Are these intersections all, or I mean, we can, I guess it's not very hard to prove that on orbits there will be singular vectors, right?
Yes.
It's kind of, I didn't do that, but it seems like it's the same proof as in some of homeworks.
It's easy to do this for simple reflections. If you go deeper, it's kind of
Okay.
it's harder actually.
And
Still
okay.
doable, but
and these vectors will be the only ones.
yes.
Okay. And it's.
This follows from Harishchandra isomorphism.
Okay.
I don't know how to see that think it's almost it's almost equivalent to Harris Chandler, right? Because these are different. So Harris Chandler map is you take center element of a center and put into correspondence its the number which it acts on the Verman module. And so actually it's like it's symmetric with respect to shifted action of web. And yeah, and yeah, it's almost equivalent, not equivalent to Harris Chandler. But okay, Harris Chandler, we saw that for SLN and proof formula for SLN. So I don't, and I think for energy is just almost straightforward generalization. You just need to spell it out in terms of its wave group and roots and weights. So yeah. Anyways, problem 5. If we have time.
Yeah, we have time, like 15 minutes.
Very well. Okay, Anthony, ask me.
How is there should be x or can we say the break and there is just
Yeah,
a number.
something is wrong.
Yeah.
No, all x such that the no, it's okay. I think.
It should be
x, I guess.
Yeah.
Somewhere.
The break
yes,
is
after
just a
that.
number.
Yes,
Okay.
you're right. Yes, the x.
Okay, so let me remember. Well, we have.
And if you could use the microphone,
Yes,
there is a potential that somebody will be happy.
Okay, so we have R tilde, which is set of alphas such that J of R, well, we have notation J alpha, but this is kind of coincides with our previous notation for modules in general. Is not zero, sorry. Yeah. And first thing we want to prove is that R tilde.
Yeah, by the way, this is experimental problem. I kind of looked at the proof of the last theorem.
W of R tilde is coincides with R tilde. So, since W is generated by simple reflections, we have sufficient proof only for one simple reflection and one alpha from R tilde, that this is inside R tilde. And to do this, we do something similar to proof in previous lecture, I guess. Well, the first claim for any V in G alpha, if we take SL2I, well, I guess I don't have to explain what does this means. Mean of V is finite dimensional. So, okay, proof. First we note that a joint of, to say, EI and or FI. Well, for HI acts on V just by number from R tilde. Okay. To consider a joint of EI. This acts nilpotently on generators or on Chevalier generators. Well, it's kind of explicit check because a joint EI taken in some, to say, power of 1 minus ij or ji will annihilate the ej with fj's it just commutes. With fi it gives hi and then it gives ei and then it gives 0, and with ei it commutes. And with hj it commutes by some number multiplied by ei and then again 0. Similar for fi. Okay, so but from this we conclude that it acts nilpotently on the whole J of R, because any element in J of R is some combination, linear combination of commutators of generators, and then using Leibniz rule or by induction, by some degree, whatever, we can prove that it's nilpotent on here. I mean that this is operator. Locally, sorry, yeah. I mean, let me just draw what does it mean. For any V exists N such that, yeah, locally, thank you, it's important, I guess. Yeah. Okay. So now what I want to do, I want first we take this n, take n1 such that a joint ei to the power n1 of v is 0. Then we take then exists some big n2 such that a joint of fi of a joint of ei to the power k here n2 of v is 0 for any k from 0 to n1, n1 minus 1, to say. Well, and this means exactly that we are done with our claim, at least. Because all vectors have form with like this, with some numbers here. And we just proved that only a finite set of them is non-zero, are non-zero. And then we do, okay, some questions to this part. Okay. So I guess I can proceed. Well.
Is it enough to take only at f to some power and e to some power?
Well, we have PBV, and we can take any order we want, and we can say, okay, here is at h to some power, which acts by number.
What it's between some powers of e or between some powers of f at h, for example?
You mean? Okay, you mean if at h here or here, yeah, or it will give us? Well, it again will act by number on this combination.
It's all weight vectors.
It's the solar weight vector. but we can say okay, just from PBV we can say that HI only here.
But you actually, like what I also want to comment is that you constructed explicitly finite dimensional
Yeah.
representation of SL2 inside.
Well,
So
yeah,
you
yeah.
go to a single vector and then create everything out of a single vector.
Yes,
So is inside some finite
seems like yes, but I use only fact that we get some finite dimensional representation of SL2, and but well, okay, yeah, sure. Then we know that it should decompose, and we have some generating vector V. Then I guess we have only one possibility, that it's irreducible. Yeah. Okay, so may I let me proceed here. Well, we do almost everything because now I want to say, okay, consider this representation. Let me denote it VI. Then what we consider our vector V, and ask what is weight with respect to this SL2. This is exactly to alpha I V, just from our definition. Then what we know, well, according to following lectures, denote this by K. Then we know that in this representation we have weight subspace V minus K, which is not 0, because Vi of K is not 0. And we know that explicit isomorphism can be only of two forms. If K is positive, this is Fi to the power K. And if K is, well, 0 is okay. And if negative, we should take Ei to the power K. And so yeah, you're right again, thank you. And then what we do, we just see, okay, let's consider only the first case, just because the second is essentially should be same. Then we just know that Fi maps not in now we are not in Vi, just in G of R should map G alpha to G alpha minus alpha I. Then this isomorphism should map V to some non-zero vector in some W, to say, in G alpha minus K alpha I, and this is Si of alpha. So so this is non-zero vector, hence this is not 0. And we proved the first part, and the second follows just in one step, I guess, because what we do know. Now we yeah. What we want?
R tilde is inside of P.
Inside.
P is
Yeah. Well. Yeah. Okay. So, but for any alpha in R, we know that exists I, W, I, okay, is number, and W in while group, such that W of alpha I is alpha. And so, then we just know that G alpha I is non-zero, just because we know that we have to say, well, plus. Let's consider positive roots, and for negatives, kind of same. Just since we have EI here. And then what we can do, okay, we know that this is non-zero, but we know that for W of this, the corresponding G will be non-zero. So we just proved for any alpha in R plus, this is non-zero, which means that R plus is inside R tilde. But for minus the same, and R inside R tilde. So we are done.
Okay, so the plan today is to kind of finish everything that I wanted to say from Kirillov, like to discuss everything. And then next time, hopefully, to start maybe doing some combinatorics related to representation theory of GLN. So Young diagrams, Young tableaus, and such stuff. Okay, so last time we proved actually we finished the classification of finite-dimensional reducible representations of semi-simple Lie algebras, and also we had this proposition that we kind of didn't finish, so maybe some couple of words about this. So that for every lambda from H star, there exists exactly one irreducible representation of highest weight lambda. And we proved that there exists at most one representation. So we have two of them of the same highest weight, then they coincide. This is just because if we have two proper submodules in the Fermat module, and they are maximal, then they should coincide. So that was our argument, but we never said why there exists one. So actually you should, again, if you take lambda, right, so existence follows from what we discussed today on the seminar, right? So if we take lambda and we take, we consider Fermat module m lambda, of highest weight lambda, then I would like to find a maximal proper submodule inside m lambda. Okay. So the question. So if I want to like to prove existence, right? I would like to find maximal proper submodule inside m lambda, and then I'm done. I'm just quotient by this submodule and get an irreducible representation. So how to construct? So we need maximal submodule, proper submodule of m lambda. And the idea was that I take all proper submodules and consider their sum. Okay, so take sum over all proper submodules. All proper submodules. So the problem is that we would like to see that this sum will also be not the whole m lambda. Then we are done, right?
So couldn't we done something with that? Like if we have two maxima, we just take
Yes.
sum and it's not whole because it don't have the highest weight.
Yes, exactly the same thing. But before we didn't know that any such submodule has weight decomposition.
So
Before today's seminar. So now we know, right? Because of problem 1. And so therefore, if it's proper, it has weight decomposition, but it doesn't include, m lambda of lambda is not inside U, because it's proper, right? And if I consider sum, then it also will not include, because all these modules have weight decomposition, and so we're actually done then. Okay, this is some remark, but also we didn't need the existence to prove a classification theorem. To construct this map from reducible finite dimensional representations to dominant integral weights, I just need uniqueness. I need just that must one, but we still can do this using today's exercise. Okay, so then let us continue. I will start with the following simple lemma. So suppose that V in some vector in Verma module is a single vector. Then if I take this vector, generate everything out of it, then what I get is isomorphic to a Verma module of some weight mu. Well, where mu is the weight of this single vector, so single vector of weight mu. Okay. This one can be proved. So like this. Let me denote actually the left-hand side by m mu tilde. Okay. So proof. Let me use Poincaré-Bergov-Witt theorem. So by PBW, the following map, well, let me call it phi mu, from U of n minus to m mu. This is just a Verma module of highest weight mu without tilde. I take A and get A V mu, where V mu is highest weight in Verma module, is an isomorphism, of course. Then let me consider this commutative diagram. I have m mu, and I have m mu tilde. I have un minus. So from here to here, I go by phi mu inverse. And from here to here, I go also in natural way. So I take A from here, and and go to AV, where V is this vector. Okay, and also I have this map, which is also natural map, just because of universal property of Fermat module. Right, so it is, so I just take highest weight vector here, maps to highest weight vector here. So there's surjective homomorphism to highest weight modules. So this one is highest weight module, of course. Yes, and this diagram is commutative. Nothing is said for now. I just would like to, so this one is an isomorphism, right? I just need to check that this one is injective. Right, this one is surjective, this one is injective, so therefore it's an isomorphism. All right, so we need to check that, let me call this somehow f mu tilde, whatever, is injective. But this follows immediately from the following. So what does it mean injective? So suppose I have AV equals to BV, then I need to check that A equals to B, right? But V is actually CV lambda for some C from U of n minus, right? And then, since I have AV equals to BV, it means that A minus B times C equals to 0. Maybe first I write V lambda equals to 0, right? But because my map phi mu is an isomorphism, I have A minus B times C equals to 0. But then it means that A minus B equals to 0 because universal enveloping algebra has no zero divisors. So, okay, let me prove that. So, A equals to B. This is follows from the following claim. U of G has no zero divisors. Proof. Again, it's a corollary of PBW. So let me order PBW basis somehow. So consider PBW basis. Right, it is of the form x1 to k1, x whatever n to kn. Right, it's every element in this form. Well, then I have this tuple of non-negative integers k1, kn, and these tuples I can order just alphabetically. Right. So order such tuples alphabetically. Anyways, we have some order on PBW basis, and this order respects multiplication. So if I take two monomials, then I mean, two pairs of monomials that I can compare, then products also will be comparable. So, but what I need actually is that let me take now two different elements, say y1, y2. These are just elements of u of g. Y1 is and y2 are not 0. Then y1 can be written like this: x1 to the k1, x2 to the k2, xn to the kn plus what I call smaller terms, right? And y2 I can similarly write x1 to the k1 tilde, x2 to the k2 tilde, xn to the kn tilde plus smaller terms. And then y1 times y2 then is x1 to the k1 plus k1 tilde, and so on, xn to the kn plus kn tilde, plus smaller terms. I guess that's what I mean when I say that this order respects multiplication. So that's it. This is not 0 then, because this will never, this term will never appear in here. I will never, cancel it. All right. So this is some exercise on PBW theorem. Okay, so corollary of this lemma is the following. Corollary. We have an exact sequence. M lambda in the middle, then I have M lambda. So here I fix lambda from P plus, which is C plus intersect P. So this is Fermat model. This is irreducible finite dimensional, and then this is sum over Fermat modules, direct sum Fermat modules Si dot lambda, where I is from 1 to R. It is direct. Without what? Oh, yeah. So this is 0. Yes, without 0 here, of course. Yes. Okay, how to prove that? It just follows from the theorem. So okay. So right, we know that from lemma. Okay, let me follow my notes, just not to invent anything on the fly. Okay, so proof. Yes, so we actually proved that well, on the seminar, I guess, we proved that M lambda Si dot lambda has single vector, right? Just choose, well, it's actually this one is a one-dimensional also. So we just choose length, right, and call the corresponding generating vector vi, right? Then by lemma, this, so u of g vi is isomorphic to Verma module of Si shifted action on lambda. And moreover, we proved, so this is a submodule in Verma module in lambda, right, by lemma. And by theorem from the last lecture, if I take L lambda tilde, which was M quotient by sum over all subrepresentations like that. So now we proved that this is just sum M Si dot lambda is finite dimensional. This finite dimensional representation of highest weight lambda, actually. And moreover, if I take irreducible finite dimensional representation, L lambda, then it is actually L lambda tilde quotient by some V. Hopefully we didn't have any V before. Right? It's just L lambda is a quotient of M lambda by some maximal module, right? So V here, yes, it's a quotient of this maximal module by this sum, right? Okay, so also this. But we know that finite dimensional representations of G are completely reducible, right? So therefore, L lambda is isomorphic to L lambda. So L lambda tilde is isomorphic to L lambda plus V.
What plus V? So V can be not reducible.
V can be, sorry, it's just because of this. And I say isomorphic, so I guess everything. Yes. We might not be reducible, but what we want is that V is actually 0, right? There was some question, I think, by Radion in Telegram, right? So actually this thing is exactly a irreducible representation. This is just because this one is highest weight, right? So you take okay, but we need again L lambda tilde is U of G V lambda tilde, right? Where V lambda tilde is image of V lambda under this quotient. And right. And also we know that V lambda tilde is belongs to L lambda under this isomorphism. If we identify under this isomorphism, right? V lambda tilde is a vector of weight lambda, and this has weight decomposition, and weight subspace of weight lambda is one-dimensional. So it's it's in either in here or in here. So of course it's in here because this highest representation of highest weight lambda, right? So therefore lambda tilde is in L lambda, right? But if I take something V from V capital, right? Since I know that it should be generated from V lambda tilde, so then V is A V lambda tilde. But then it is inside L lambda, right? So this is inside also in L lambda. So therefore V is 0. So therefore V capital is 0. Andrei, you were confused.
Yeah, is this true that we can proceed without using reducibility? I mean, kind of statement of the kind that if we have just finite dimensional representation of some highest weight, then it should be reducible.
That's basically what we do here.
But here you say that we use reducibility of finite dimensional
Yes.
representations, and it's kind of long story to prove.
Completely reducibility, you mean?
Yeah.
Yes. Well, I assume that we proved it using some homological algebra, some number of lectures ago. Yeah.
I'm saying that I guess we can do everything without using. I mean, if we.
Might be true. I don't know. I'm not sure how. What for now, but it might be true. It's an easy statement. Maybe you don't need like. But it's since we have it anyways, so why not use it? Yeah. Okay. All right. So the story is that this is a part of actually what's called Bernstein-Gelfand resolution. And let us just present it, look at it, and be happy, because I mean, it's Yun Kirillov. He actually refers to original paper, and if you look over the internet, I found only one attempt to actually rewrite it in modern terms, which actually you need to know like category O, like it's a lot of things that you need to know and use. Right. So, but it's useful just to know that such thing exists. Okay. So. So the BGG resolution is a resolution of finite dimensional reducible representation by direct sums of Fermat modules. Okay, so it exists and it has concrete form. So let me denote this as, I don't know, star, and say, okay, sequence star is a part of what's called Bernstein-Gelfand resolution. Sometimes it's just abbreviated as BGG. Resolution And it goes like this. Okay, so beginning is like there. And then you have Fermat module. Then you have direct sum of SE acting on lambda. But then next, so I will just write like a general term in here. It goes like this. It's a direct sum over all elements of the while group of length, of some fixed length. So this is kth. So if I start counting from here, it is a kth element of this sequence. Okay, so this is k. So length of this is 1. And here I have m, w acting on lambda. And then I continue. And then I have w0, where this is the longest element. That we know that it goes, it maps C plus to negative C plus. And then 0.
What are the differentials?
Differentials are, well, you find single vector, like single vectors inside, and generate everything out of that. And this will be, so this will be submodel which is isomorphic to model that you map.
So like
There.
MSI lambda, it's you can find there a lot of like MSJ, SI lambda, yeah.
Yes. So the thing is that actually this sum here, where it is, yes, over there, it's not direct, right? So these models, they intersect somehow, right? And so they intersect in some sum of Fermat modules, right? And single vector from which you construct them, generate them, they are in length 2 shifted action of Weyl group. But this sum is also, they have some intersection. So, and so you just continue.
I understand correctly that the miracle there are no multiplicities.
There is no SI.
No multiplicities we have. Take for example this m w multiplied by lambda with some in some power. For example, we can take it twice.
Yes, this is of course important, but also so there it's explicit elements in each term here, right? Of course, you can try to cover like every time try to construct some by some Fermat modules, right? So I guess you also miracle that you stop at some time. Yes. Okay. Yes.
Is this resolution in sense which we discussed before? I mean, these all modules are projective?
Well, yes, they turn so finite dimensional models are projective, yes. But Fermat models as well, yes. I think like a category O is a nice category. work with, and Verma modules stay inside. Yes.
Wait, they're projective? So it's like modulus over C, or U of G?
Over U of G, yes. So I don't know. This category theory language I don't want to make any statements. Yes. So because I just don't know. Yeah. But are they projective?
So we should be able to lift highest weight vectors, right?
Lift in what sense?
We have some morphism of modules,
Mm-hmm.
and what does it mean to have morphism from Verma module? It means
Mm-hmm.
to have highest weight vector.
Yes, yes.
Projectivity is essentially lifting of morphisms from Verma module. So now lifting of highest weight vectors.
Yeah, but you might resolve not only by Verma modules, actually.
Yeah, I mean if we asking about projectivity of Verma modules.
Ah.
Can we list this?
Is it true?
I don't know how. I guess we should use these restrictions, which called by category O, but I don't remember. It includes local nilpotency.
Yes, the, local nilpotency, and I need weight decomposition also.
What is category 4?
Yes, so it's all modules such that, SL2 triples act locally nilpotent, if I remember correctly, and it admits weight decomposition. Maybe something else that I forgot. No. There's example of zero, like some that's not. So abelian means also means semi-simple, right? No.
Kernels, co-kernels, and
Yes.
and the isomorphism of
So
the theory of that.
Well, there's like for morphisms should be abelian groups. There should be zero elements. There should be like kernels, and coimage should be equal to image. Yeah, all like that.
okay, whatever. I don't know. So I'm not authorized to answer such questions. So I don't know. All right. So another thing that we have to discuss is characters. So let's characters of representations. Yeah, so let me consider, so these are objects of what? So I would like to consider H star as an abelian group and consider group algebra of it. So as an abelian group. And consider, well, it's more than, but we just need this, and consider its group algebra that I would like to realize as finite sums like that. Right, so it is finite sums, formal sums of the form sum with some coefficients times such symbol, well, e to the lambda, as lambda runs over h star, and here a lambdas are complex numbers, right? So we can actually multiply them if we put that e to lambda times e to the mu is e to lambda plus mu. Yeah, some symbol, if you wish. You can make it more precise, I guess, but no, it's fun. Let's just think of it as it's just formal symbol, and they are multiplied like that. Then we also need we will also need characters of some infinite dimensional representations. Well, Verma modules. So I need to consider something more than that. So let me denote it like that. So it's some completion, if you wish. So these are formal series of the form sum a lambda e lambda, maybe replace this by mu, where mu is less or equal than some fixed lambda. So this will be enough for me. Yes, and then character is so let me take v to be some representation of highest weight, or finite direct sum, maybe, or finite sum of representations of highest weights. And then let me define character of v that will live in here as follows. It's sum, and then these coefficients are just dimensions of v of mu, e to the mu, as mu runs over h star. No, it's not. It's not from here. I should fix something, right? For finite, it's like I don't need too much, right? I just finite linear combinations or finite sums of formal series of the form like this. So yeah, if I can have in practice, I can have two different highest weights, right? They might differ by something, not by root, for example, at all. So we'll have just sum of two series of this form.
So you should add completion there, right?
Yeah. Not really. I write something like mu less or equal than lambda here.
I mean, so you mean we have lambda on the left hand side, or we have this for some lambda?
This is for some lambda, I meant.
Don't we have, if we have a finite number of roots lambda like this, we can have a big enough root that is bigger than all.
Lambda can be not root, it can be some just element of H star.
Yeah, but can we just
H star.
No. I can take two highest weight representations of two weights which do not differ by anything from the root weights. This will not be of such form. It's stupid, but I have to fix it somehow. Okay. Yes. All of that is just to have character of Fermat module. Yes. Proposition. Character. Of m lambda is E lambda divided by product of alpha in R plus 1 minus e to the negative alpha. So this 1 over this I should understand as the following series. It's just 1 plus e to the alpha plus e to the 2 alpha plus and so on.
Why do people sometimes use trace notation for check?
Because if you consider group and corresponding torus corresponding to Cartan subalgebra, and you take traces of over some representation of this corresponding representation, you can relate it to this thing. So basically, Tor, like it's diagonalizable, right? And if you consider trace, it will, in corresponding basis, it will be exactly like this.
And the exponent will be real exponent.
The exponent will be a real exponent, yes.
So the 1 over 1 minus e minus alpha.
Yes, so sorry. Should be something like this, yes. Yeah, so the proof is clear. So we just need to just some elementary combinatorics, right? We just need to look at denominator, right? Denominator is what? It's just 1. Let me just expand it. 1 plus e to negative alpha 1 plus e to negative 2 alpha 1, and so on. Then 1 plus e to negative alpha 2 plus e to negative 2 alpha 2, and so on, and a bunch of terms like that. So this is actually can be written as 1 plus sum e to right, to the negative alpha, where alpha runs over what is called Q plus, so positive part of root weights. So let me So Q plus is it's just sum over mi alpha I, where mi is greater is integers which is greater or equal than 0. I from 1 to r. And of course some coefficients should be here, right? And what is this coefficient? It's clear, right? So where n alpha is a number of ways to write alpha, right, as a sum of like this. So I runs from 1 not to r but to some n. I'm using notations from today's seminar. Okay, so these are all positive fruits. Well, you just look at this product and understand, right? So you just need to choose different. So so if you have an I here for n1, right? You take nth term here, right? And first term here, and second term here, and so on. And this will give you bijection between these n's and choosing terms from each. Yes, and this actually proves everything, right? Because we know that dimension. So this is exactly the dimension of m lambda of weight subspace of m lambda of weight lambda minus alpha. Yes. And okay, another proposition, which is also kind of clear. Proposition. Suppose we have an exact sequence of representations of G I should again which representations of highest weight, if you wish. I just would like to those representations for which I can write a character. Okay. Yes, to write character. Yes. Okay. Anyways, and then you have such exact sequence. So then, of course, character. Then you have a relation for characters, which goes like this. You take character of vi, and organize alternating sum, and this is 0, right? Okay, I think just some linear algebra. And I need this to actually use BGG resolution to write down the Wales formula character formula. So character of L lambda equals to the sum, right? -1 to the power L of W e to the W dot lambda over Weyl denominator. It's called product over alpha from R plus 1 minus e to the negative alpha. So this is called Weyl's character formula. And we have seen such thing and actually proved it without any BGG resolutions for SLN. And you can do it in the similar way here. For BGG, for SLN, what we did, we used Harishchandra actually. And we that was, so we actually each time covered single weight. Each time we generated from a single weight Fermat module and quotient by it, and then quotient by it. But since we know that all single weights are only in the shifted orbit, there's only we reduce dimension of weights where we can find single weight, and so we stop at some time. Okay, that was the argument that we used, but for that you need Harishchandra, which is also you have here. So I just don't see like a big point to repeat all this. So what's important to look at BGG, at least a statement, and see that Weyl's character formula follows from it. Okay. Finally, I would like to. So we will apply characters more, but so in general, characters can be used to decompose, right? Like so, say tensor products of representations into irreducible, or finite dimensional into irreducibles. So let me. Okay. Right, so let me actually introduce, of course I have weight lattice, which is also a abelian group, right? And it has its group algebra, right? Which is finite, again, sums of the form, this, right, a lambda e to lambda runs over p. And what I need is that Weyl group acts on C of p. Right? Of course, it acts on H H star are attacks, right? But also attacks on C of P as well. Also, well, it's clear how it happens. So if I take an element, sum like this, right, then the corresponding action is just sum A lambda e to the W of lambda. And proposition that I will need is that if I take all characters of L lambda, as lambda runs over P plus, then it is a basis in where? In all in all elements C of P which are invariant with respect to action of Weil group. Okay, proof. We just take some obvious basis, which is this. So consists of elements of this obvious basis is just what's called orbit functions. It's sum W of lambda over W over elements from the Weil group. Right. As lambda runs over P plus. So this is a basis, of course, of C of P W. Right? Well, just because C plus is a fundamental domain for the action of Weil group. Right? If you have a point there, and then you have all reflections of these points, all the images under the action of Weil group. So this is actually basis. And of course, if you can write characters of L lambda, so if lambda is in P plus, so character of L lambda, it is in here, right? Right. So all multiplicities and weights are well invariant, so it is in here. So this is m lambda plus sum over mu less or equal than lambda over m mu's with some coefficients. I don't know, c mu. So actually, we can switch between L lambda and m lambda by upper triangular matrix, if you wish, right? With ones on the diagonal. So this is actually why L lambda is basis in here. So once you have this, well, you can now recursively express back m lambda from characters, right? So from this we already can understand that B, right? B is so let's call this B, is linearly independent. But then you can use this because it's like a triangular of triangular form. You can express m lambda back from characters. And it means that actually B spans C of PW. These are just some numbers. We do not specify. Right, and from yes. No. Characters are symmetric with respect to usual action. Because weights, because we have this dimension of V of lambda is the same as dimension of V of W of lambda, right? For finite dimensional representations, of course. Did I? No. Where? Maybe I wrote. This is part of Weyl formula.
Yes. So isn't we using like this character for lambda to span all?
We are not using Weyl's character here. So to say that. Okay, why is this true? First of all, I'm using this, and I'm using the dimension of L lambda lambda is 1. That's the only two things that I use. Okay. So I just take my P plus, right, and take all points, all weights in there from L lambda, right? So then from this I generate M lambda. So this is lambda, right? So since I have symmetry with respect to Weyl group, I have M lambda there, but also with coefficient 1 because of this. But also any point here gives me some other M mu because again of symmetry.
Is this true that terms in this formula for the character are in one-to-one correspondence with weights in fundamental domain?
Yes. Yes. Right. So these are actually some dimensions of weight spaces. Right. So from 1, we can recursively express the M lambda back from characters. Sum over characters of L mu. I think I should introduce some notation. Let's call this high mu. I'm kind of tired to write L lambda all the time. Right? So this means that B spans C of P W, and we are done.
lambda is character of
yes. So I would like to use this. So how do I proceed? Yes. So I would like to take yeah, it's recursive. Yes, I just so I take m0, right? I start recursion, right? Of course, it's just the same as high 0, right?
We should add some coefficients to form your.
Yes, you're right. Yes, so mu less or equal than lambda, and here some c tilde, I don't know, mu. And then I say, okay, let's suppose that I expressed all high mu, all high mu, right, in terms of m mu's for all mu less or equal than lambda, right? Then this formula says, then I actually express m lambda as well.
all lambda and mu are
From p plus, yes.
then it works.
Mm-hmm. Okay, so right. So one last thing to mention is that the following. So let's just state that we can use characters to decompose tensor products. So high lambda times high mu is sum with some coefficients n nu high nu, sum over nu, if and only if L lambda, right? So here nu over p plus, and lambda mu here also are elements of p plus. L lambda tensor L mu is a direct sum over nu from p plus and nu L nu. So these are multiplicities, right, of corresponding. From here to here, it's obvious, right? From here to here, we use the proposition, right? So first of all, so from here to here, okay? Proof. So actually, if we take tensor product, then it decomposes somehow with some mu m nu, right? Nu is from p plus for some m nu. Therefore, we have that high lambda times high mu is sum decomposes in the following way. But this means that m nu is equals to n nu, because high nu is a basis.
Yeah, and like n nu L nu is direct sum of L nu n nu times.
Yes, yes.
So there's always it always should be integer. No.
Yes.
Natural.
All right, so this is, after that I wanted to start some combinatorics related to representations of GLN, but I mean, next time. Okay, so let's stop here.